Welcome everybody to the beginning of section 5.3. We are looking at page 110 in the workbook, and the topic of this section is matrix limits and Markov chains. And this material is about something called a stochastic process, where we're essentially studying elements of a set that can be in one of a finite number of states, and there's some predictable way that these elements are transitioning between one state and another. And we'll be interested in questions like predicting what is the distribution of these elements going to be after a long time goes by. Okay, we'll discover that we can model a situation like this using matrices, and that being able to raise matrices to powers is going to play a fundamental role here. So let's start with an example. Okay, so example 1, let's read the question together here. Suppose that each decade 10% of the people living in the US but outside of California move to California, and 20% of the people inside of California move to another state in the US. So we've kind of got two states that our population could be, either inside of California or outside of California, and they've given us some data as to how the populations are migrating between these two categories. Okay, and we'll also assume that we have a starting population in California of 30 million, and the rest of the country is 270 million. This data is probably a little bit out of date, but we'll go with it. The numbers are nice and round here. And let's start out by looking at part A together. So it would like us to find the populations of California and the rest of the US after 1 and 2 decades have passed. Okay, specific amount of time here that we're going to look at. All right, so let's start by just giving names to the categories that we have. I'm going to use XN to represent people outside of California and YN for people inside. So XN is people outside of California after N decades. Okay, and YN is going to be people inside of California after N decades. And we'll be consistent with this notation for the remainder of the problem. All right, so let's start with N equals 1 decade. Okay, that was the first thing that they wanted us to find the populations at. Okay, so X1 and Y1, those would be the populations outside and inside of California after 1 decade. And just to remind you of that, remind all of us of that, okay, we'll put an out and an in there. And so starting with the out, we could ask ourselves the question, the people who are outside of California after 1 decade, where could they come from? Well, really, only one of two categories: either the people who were already outside of California at the beginning, or people who were originally inside of California. Okay, and the same is true when we jump down here to Y1, the people who are inside California after 1 decade, they could either come from those who were outside originally or inside originally. We just have to figure out the percentages in each category. All right, so let's start with X0, and remember, those are the people who were outside of California at the beginning, so living in the US but outside of California. The data tells us that 10% of them belong down here, okay, because they're going to move outside of they were originally outside of California and are going to move in. And the other 90% are going to stay outside. Okay, that's what that first part of the sentence is telling us. And then we move over to Y naught. Those are the people who are inside of California at the original state, and how are they behaving? Well, 20% of them are going to move outside, and the other 80% are going to stay in, according to our data. Okay, so that's our state of affairs so far, and we can now proceed to calculate these numbers. Okay, so going back to our original data, they tell us that the original population of California is 30 million. Notice that that's Y naught. And the rest of the US, 270 million, that's X naught. Okay, so we can fill in those numbers and just see what we get here. Okay, so 0.9 times 270 plus 0.2 times 30. Okay, you can double check my arithmetic. That winds up being 249. And down here, 0.1 times 270 plus 0.8 times 30. That's going to be 51. All right, remember that our data is in millions. So if we kind of put that into a sentence, after 1 decade, we have 249 million outside of California and 51 million in. Okay, so we can kind of see that our California population has grown considerably and the rest of the population of the US has gone down. Okay, so that's where it looks after 1 decade. And the second part of the question is, well, what happens after 2 decades? Well, the good thing is we're kind of going to repeat the same process. Okay, so we're looking for x2 and y2 now. And again, remind ourselves that x represents outside and y represents inside. And kind of the same situation is true. Those people who were outside of California after 2 decades, they can either come from people who were already outside after 1 decade or who were inside after 1 decade. And the same is true of y2. And if you think about it, the percentages should be the same too. It's still true. Okay, these 10 and 20% numbers, migration numbers that we had above, those are still true. So we should still get the 90% and the 10% there, and the 20% and the 80% there. Okay, we're just talking about 1 decade farther in the future now. Okay, and so we can do this calculation again. X1 and Y1 are going to come from our calculations up here in the first step. All right, so we're going to fill in those numbers for x1 and y1, and here's what we wind up with. Okay, so 90% of 249, that's x1, plus 20% of y1, which is 51, and down here, kind of the same thing. Those are numbers that we can calculate, and I'm just going to show you what I ended up with. You can check my arithmetic. So up here, 234.3, and down below, 65.7. Okay, so we have answered the first part of the question. Okay, what the populations are after 1 and 2 decades. Actually, let's write a quick sentence, like we did up above. So after 2 decades, we're just saying 65.7 million in, okay, and 234.3 million out. Okay, I'll go ahead and circle those just to emphasize that those were our answers to the first part of the question. And now we're ready to move on to the second. So they'd like us to use a matrix to model this situation. Okay, kind of a matrix naturally falls out of this. Okay, so in general, here's what we could observe. Okay, so xn and yn, let's put those into a vector here, and notice that we can calculate that by taking 0.9, 0.2, 0.1, 0.8, and multiplying it by what the populations looked like at the previous stage. Okay, do you see where those numbers are coming from? The 0.9 and the 0.2 come from there and there, and the 0.1 and the 0.8 come from there and there. If you go up and just kind of examine the calculation that we did up here, we could do that same calculation using the matrix multiplication that we did down below. Okay, and this matrix, I'm going to give the name A. That's called the transition matrix. Okay, it's a matrix just gives us information about how we transition from one state into another. And notice too from above that we kind of multiplied by that matrix one time to get our data for x1 and x2 up here, and then we just did that again to find our data after 2 stages. So there's an iterative process here. We keep multiplying by the same matrix over and over again. So we could continue this calculation and say that if we take that matrix and square it, we could multiply by data 2 decades ago, and it should tell us what's happening after n decades, and this process just continues and gets us all the way down to a situation where we can take that transition matrix, and if we raise it to the nth power and multiply it by our original population data, it should tell us what's going on after n decades. Okay, so here's the general formula that they were asking us about. Okay, and just to kind of summarize it, put it all together from start to finish, is just saying this. If you want to know what the population distribution is after n decades, that would be this vector up here. It's just saying you're going to take this transition matrix and do it n times, basically. Okay, you're going to multiply it by itself n times, multiply by the original data, and that should tell you the state of affairs after n decades. Okay, and the problems that we do in this section are all going to kind of have that flavor to them. Okay, so that was kind of a long process, but I think we're ready now for part B of this. Okay, they'd like us to find the eigenvalues of this matrix. That's going to turn out to play kind of a pivotal role in problems like this. Okay, so we know how to find eigenvalues. Let's just review the process here. So we'll form the matrix A minus lambda I. Okay, we'll take that determinant. Okay, and 0.2 times 0.1 is actually 0.02. Really, the only thing different here is that our numbers are not so nice. We've got some decimals involved. Okay, but the process is the same. So see, if we do our multiplication, we'll get 0.72 middle terms minus 1.7 lambda plus lambda squared minus 0.02. Then we might notice that we can take the two constant terms and put them together. And rewriting that, that's going to give us lambda squared minus 1.7 lambda. Subtract those, and we're going to get a plus 0.7. And we can factor this, even though we've got decimals involved. Okay, this is going to factor into lambda minus 1 and lambda minus 0.7. Okay, so you can see from that, if we set that equal to 0, we've got two eigenvalues. Lambda equals 1 and lambda equals 0.7. Okay, and in the next video, we will continue with this very long problem and see how those eigenvalues can help us, okay, to continue answering questions about this population pattern.